guys. So for today's lesson, we're going to go over just a little bit of review. This should all sound pretty familiar to you, but we're going to go over just some graphing reviews. So by the end of this class, you should be able to use data. You're going to have some practice data to work with to produce a graph and then use them to analyze the results. So I'm just going to go over a little bit of a couple of different graphs and a couple of different things that you'll see in our science classes, and we'll go from there. So we're just going to follow the step-by-steps of how to set up a graph. So step one, make sure that you title your graph correctly. If you're looking at a graph based on, plant growth, you're not going to title it something having to do with the soil. You're going to title it plant growth over, let's say it's over time. You're going to say plant growth over the month of August or something like that. You want the effect of the independent variable on the dependent. So the effect of fertilizer on plant growth. That would be another great way to phrase it. So step two, you're going to correctly label the axes of your graph. So the x-axis always represents your independent variable. Your y-axis always represents your dependent variable. So that's why it's really important to know what your independent and your dependent variables are. In science, time will often be your independent variable. So if we're measuring, how long it takes to do something, that would be your independent variable. You want to make sure that you label the units on your axes correctly. If you're working with time, make sure you label it as minutes or seconds or hours or even years. Don't forget to label it or don't label it totally incorrectly. You need to make sure that they always have labels. Temperature, again, in science, it's going to be most of the time degrees Celsius. And then distance, you can measure it in meters. Okay. So the next thing you want to do is you want to figure out what type of graph you're going to use. There's a couple of different types of graphs that we can use in science. You can see we have a couple of different ones here. So the scatter plot, it's the most common in science. It allows us to see trends between the independent and the dependent variable and then kind of fill in some missing data. So if we have this scatter plot here and we have these dots kind of all over, you would not want to try to turn this into a line graph and, connect every single one of these dots. This is a scatter plot where you're going to draw a line of best fit. So we can go into more detail with that. This is easiest to do on a computer because you can plot all your points and then you can go into line of best fit. And if you're going to be doing this on the computer, you can actually watch another video that we've created that tells you how to do this. Another option is bar graphs. It just allows us to compare categories. You have pie charts. These actually don't have axes. It's just going to be breaking into smaller categories. And then a line graph, another pretty common one used in science. And it allows us to just track the change of something over time. So how do you figure out the scale of the axes? The scale should be even for both of them. And it should include the range of your data. So we have two questions here. We have minutes, and we're going up to 6 minutes with our speed of a cheetah. Let's go back. Our speed of a cheetah, and then so you have minutes and miles per hour. So what I want you to do is kind of write down in the answer box what you believe would be our scale for this one. So we have, it goes up to 6 minutes. So do you think we would want this to go up to 6,000 minutes? Probably not. And then we have our speed of a cheetah, which goes into miles per hour. The fastest speed is going to be 80. Slowest is going to be 35. Then we have our next question. Inches of rain. So what about here? How would you set this one up? So I want you guys to just kind of put your answers in and we'll go from there. So this is our example. You guys should have put in what you thought would be our scale for our last one. But we're going to go over what we believe this graph should actually look like. So you have inches of rain. You have 12 up to 110. So we started at 0 here. Notice that We have our inches of rain down here on this x-axis. We don't start at 12, we start at 0. And we're going by 5s for this scale because we want to get up to 110 as our last data point. For our scale on the left-hand side, the y-axis, you have numbers of mosquitoes. Again, you're starting at 0, but you need to get up to at least 15,000. We went a little higher than that and went up to 20,000. Okay? So you want to make sure that they're plotted evenly and are able to encompass the entire scale of what we want to look at. So there's a little bit more about the best fit line. So it's a straight line that goes through the center of your data. The equation of the line is very helpful in data analysis, but you're not going to be connecting all of your dots. Again, if you want to see how this is done on the computer, you can watch one of our other videos. So I just want to show you one more thing. And these are just what I consider bad graphs. So again, graphs, they're a way to turn kind of abstract quantitative data into something that you can look at. It allows you to look at like a picture or something like that. So this is what I would consider a bad graph. You don't really have a title, regulated, unregulated. What does that mean? We know nothing about what that means. You have a little bit of a key over here, really not telling you anything. They did not put a scale at all. And then they have kind of just by rounds. It's not evened out. It's not equal in any way. This one we would consider an okay graph. Again, there's no title. There's no key. It doesn't tell you really what's going on. They do have both axes labeled, which is great. But we really don't know what they're measuring at all. It says species, but then we've got M&Ms and red licorice and all of that. So we don't really know what's going on. This is a much better graph. Still not perfect, but we're starting at 0. We have everything equaled out evenly. We have a scale to the left here, but we're missing